This is the fourth and final part of color perception. So I'm leaving this slide the way it is, even though you can't share your experiences with people and you can't hear other people share their experiences, but I do want you to think about your experiences of color vision. I think it's a really neat thing that we have and that we do experience it differently from each other. I'm going to share Mr. I's story, which is on a different page now. I'm sorry, I did not update that. But Mr. I was a person who received some, a bump to the head, got some brain damage in the cortex, and ended up with a cerebral achromatopsia, where A meaning not, chroma meaning color, so losing his color vision. And cerebral meaning it's because of damage to the cerebral cortex. And he was an artist, and this damage ended up causing a great deal of depression for him, partly because of his art and not really knowing what to do or how to handle that and how to adapt to that. But there were other things as well, and part of the story of Mr. I is that for a while he would eat things like black beans and rice because they're already black and white, and he would say things like, you know, orange juice looks weird gray and I used to be able to see my dog outside, but now it's only the movement because the dog doesn't kind of pop out from the background anymore. So just that we're using our vision, our color vision, for a lot of things, a lot of our experience, and there are things that we expect. I mean, we talked about taste and flavor and that experience of food, so that's going to change, right? If you've just changed your now I don't see color. But my understanding is that he did adapt. He did learn to start eating more than just black beans and rice, and getting used to the fact that these things no longer had the color that they used to have. And he started doing, he was already kind of an abstract artist. He started just working in blacks and whites and shades of gray because that's what he could still really see and understand. So this cerebral achromatopsia, and I can't remember if I included this article in the e-reserves, but there is an article that's looking at achromatopsia. There's lots of research looking at achromatopsia, which is so that A meaning not, chroma meaning color, lacking color, so really having a monochromatic world, which is an achromatic world. It's just blacks and whites and grays due to damage to the cortex. They do appear to have some experience still of wavelength. Their cones are still sending that information to the brain. They're just not having the experience of perceiving this as color. So the suggestion is that maybe they have more enhanced senses of the differences in gray, because again, they're getting the wavelength information from the cones. If we ask what we know about color in the cortex, I'm going to say these 4 things, but it's going to feel like, well, not much. We know that there is not a single module for color vision. There was suggested to be a single module by, I think his name is Zeki, quite a while ago, partly because of people who have achromatopsia, but it looks like it is very distributed processing, and we're going to see a piece of research looking at this very distributed processing. We know that some cortical neurons are still responding to just some wavelengths as we keep some of that information, especially from the short wavelength cones, really separated from the long wavelength cones through the lateral geniculate nucleus and up into the cortex. In many areas of the cortex, including in the primary visual cortex, so in V1, and in the ventral stream for object recognition, some of those neurons still have opponent processes. I actually have a really fun, what's it called? Illusion kind of thing where you kind of see a box and you have those illusory conjunctions, even though there are these pieces taken out. And if you look at that for a long time, and I think it's colored purple or something, and then you look to the white splotch, instead of seeing the circles taken out, you see the whole box. So you're filling that in. So it's not just that these opponent processes occur at the level of the retina, but they are occurring. These opponent processes are occurring at the level of the cortex and in the interpretation of what I'm seeing. And we also know that neurons that respond to color also respond to form and orientation. So form, orientation, color, all of these things inform us about the objects in that what ventral stream. So in this fMRI study, they asked people to look at these different blobs. And in A, we're showing the blue in the brain. Basically, I'm deciding, do they have different textures? For the green colors in that brain, I'm deciding, are these different colors? And for the red areas in that brain, I'm deciding, are these different shapes? And so we can see that there are various regions responding to those different things. But the yellow, so notice, put together the green, which is am I seeing different colors, that decision, and the yellow, which is the color mixed with that and either one of the others. So color, perceiving color and distinguishing color is very distributed in all of those green and yellow areas. We see those areas lit up or active in response to that question of, are these different colors? So it's very distributed processing. And we might ask how? How do we get this cortical damage that causes achromatopsia? And I have this as a green question to think about. But the answer really is that we don't know. The scientists don't really know. And interestingly, again, I can't remember if I put that article in the e-reserves, but interestingly, if I have a complete achromatopsia, I'm lost my color vision because of damage to the cerebral cortex, oftentimes they also see prosopagnosia. If you remember what that is I am unable to recognize faces because my fusiform face area is also damaged. So it appears to be what we might think of as a module, but it's not, because it has this distributed processing, is close to that area that is responsible for me really perceiving and recognizing faces. One of the final things to talk about with color vision is this experience of color constancy and lightness constancy, that we have these perceptual constancies, which we talked about with phonemes, but we have this with color vision as well. And if we look at, so I'm going to take that middle example in B. If I'm wearing green and it's basically reflecting these about 520 nanometers and around that area, so I'm reflecting some of the lights in that in those medium wavelengths and not the short or long wavelengths. What happens with that reflectance curve if we look at, so if I go to A and look at, usually we think of it as being across the electromagnetic spectrum because this is what I'm reflecting, and so across the electromagnetic spectrum, what's being shown there in white or sunlight, I'm going to keep that same reflectance curve, but we have different kinds of light. We can go into those tungsten lights or incandescent lights where they are illuminating more with longer wavelengths of light, or we can walk into what we have a lot more now, these LED lights, where they are illuminating more with the shorter wavelengths of light, and those should be shifting that reflectance curve around, right? So what's being shown in C, if you'll notice, we've cut off from 400 to 600 nanometers now, so we've cut off a little bit of our curve of the reflectance curve, which is why it looks different. But so under white light, that white bar or graph, piece of the graph is very, very similar to what we saw with the green, but we are shifting that with the tungsten lights to the point where it should appear more yellow, maybe even a little bit red. And in the LED lights, we're shifting that down where it should appear to be a little bit more like blue, but that's not what happens, right? Green stays green regardless of which light I'm walking into or out of. If we ask why this happens, well, in one study, they showed that to some extent, we have this partial, or this chromatic adaptation that partially gives us color constancy, that our eyes are under the same light as whatever we're looking at. So here they had people looking, Uchikawa and colleagues had people looking at a green piece of paper. And so the paper itself is not informative as to what color I should expect. I'm just seeing this green sheet of paper, and the baseline is it's under a white light, and I'm under a white light, and I'm saying my perception is paper is green. If they put the paper under a red light and my eye is under a white light, it shifts the appearance of that paper to be towards red. And if they put the red light on the paper and my eye is under that same red light, now we have a very slight shift, but not to the same extent as if my eye is under a different light. And so now it's a little bit more yellowish, but it's still kind of green. So this doesn't really explain color constancy, but this kind of chromatic adaptation that my eyes are adapting to that same kind of light or color illuminant gives me a partial color constancy. But there's more to color constancy. And so this is where I bring in Retinex theory, but your authors basically dance around Retinex theory, this idea that the cortex is taking into account that context. It is making comparisons across the retina, which is how that gets its name, from the cortex and the retina. But so I have these question marks, but really it's all of these things are included. So the surrounding environment, and you can see that these different blocks, I mean, maybe, so is this a green block in the back that gets shifted towards yellow depending on what light I'm under? But partly that is the illuminant, and partly that is probably has something to do with the context. Or is it shifted, or is it yellow and it's more shifted towards green depending as I'm getting towards blue light? It's not completely clear in these pictures. The nice thing about these pictures is that surrounding environment, it's still the context or what's hitting your retina, but the images themselves, the objects themselves are not informative. We also have a memory for color. So in one study, they showed gray bananas with no coloring on them on a gray background with slightly different grays so that you could distinguish the bananas from the background. And they asked people to report the color, and people reported that there was some yellow in those bananas even though it didn't exist. So that memory for color also influences what we see. And so if we take all of that together, that chromatic adaptation of our eyes, we're taking into account the context and the surrounding environment. We're also using our memory for color. That gives us color constancy. We're putting all of that together for color constancy. And the journal article that, I'm sorry, I don't remember if I put in those possible reads, and if anybody wants to read it, it's very complicated because what they're doing is they're looking at several different people with brain damage, and some of them, or a couple of them, have a real complete achromatopsia, but some of them have these more specific and unique areas of damage. Like one of them, they can't remember color names. One of them, they can't remember what color bananas are, and things like that. So we can have these more interestingly different kinds of difficulties with color. And I'm going to introduce or talk about just a couple of pieces of lightness constancy. I'm not going to go quite into as much as what they have in the textbook, but so we maintain a certain constancy for these achromatic colors as well, so black to gray to white, that are across the electromagnetic spectrum. And it looks like what we're really doing is, and again, if you think of it as the Retinex theory, that we're using the context and we're making comparisons across the retina, that we're using this ratio principle. So if my white spaces are reflecting 90% of the light and my black spaces are reflecting 9% of the light, I'm under 100 units of light. The white's going to give me 90, the black's going to give me 9, and that's going to give me that that ratio of 90 to 9, that's going to give me the white and black distinction. And I can take that same checkerboard out to my 10,000 units of light out in the sun, and now that 90% is 9,000 units for the white, 900 units for the black, and you can see that the black under the sun, so that 900 units is actually a higher amount of light hitting our eyes than we were under the 100 unit light when we were looking at white, right? Because my illuminant is that much brighter, and yet we have that same ratio. Now it's 9,000 to 900, but we can bring that down to a 10 to 1 kind of thing. So it looks like we're using this ratio principle. And what's also really kind of neat about lightness, constancy, and we can think about how top-down knowledge influences some of this, is that the perceptual system has to make these distinctions, and we don't seem to have any problems making these distinctions between reflectance edges, so where the amount of reflectance changes, right? So we have two different surfaces that are reflecting different amounts of light, versus illumination edges, where it is about the illuminance, or the amount of an illuminant that is hitting those surfaces. So if we go from A to C, we can see that C is darker, but even if we go from B, which is under shadow, and we see this illumination edge, to C, which is a darker part of the building, but under a lighter, under more illumination, we can still see that B is lighter than C. Like, our perceptual system can do that, even though, again, what's being reflected into the eyes, we should see B appears darker. And it does, but it appears darker, but we know it's a shadow. So we know that the reflectance edge, or the reflectance, is lighter. All right, always hoping those things make sense. And I'm going to go ahead and stop there. I usually do a teeny bit about top-down processing. Well, let me do one more picture. I'm going to skip some things and do one more picture. All right, I a little bit lied. I'm going to do two more little tiny things. So here's a picture of just, again, thinking about top-down processing, or how we're using, so think about how we're using top-down processing to interpret shadow in these two different examples. All right, so top-down processing, my background knowledge, my experience. And that's a good thing to pause and practice. And my final little thing to go through is to recommend this video, which I will put out in Blackboard. It is a very short video that includes optical illusions that are fun, and it relates back to color, and it's really short, so it's fun. All right. And my very last thing to do for this is to come back to these questions, which, again, I hope you're doing this pausing and things for these different questions and green questions and watching the videos, but do think about, what does color do for us? We went through some of the functions. I'm going to actually answer some of these. What physical attributes of the object influence its perceived color? I ask this every semester, and I get some pretty good guesses and things to say, but what I'm really looking for is the specific wavelengths that are being reflected versus absorbed. Those are the physical attributes that influence of the object itself, that influence its color. An object that is reflecting some wavelengths and absorbing others. We can ask, what physical attributes of an object's environment influence its perceived color? And you might go back to that Joseph Albers picture and just think about, or that little short video is really neat, as far as really thinking about how we use context and assumptions about shadows and things like that. All of that's fun to look at and think about. And then describing our color experience. I don't know how to ask you all to give me some of this through Blackboard, but it is always interesting to me. There are a lot of people who talk about color and think about color very differently than me. And there's lots and lots of research on color, and I know there was somebody in this class who did a neat, looked at a review article examining many aspects actually of color processing, how it affects us, how it affects our cognition, affect, behavior, all of those things. So pause, think, reflect, share if you're willing, email me, whatever.